Two different systems were created. One imperial in North America, created by the former Longyear, now called Boart Longyear, and one metric in Europe, created by the former Swedish Diamond Rock Drilling Company. The imperial system is commonly referred to as the DCDMA Standard, or Diamond Core Drilling Manufacturers Association, and the metric system is called CMS, or Cralius Metric Standard. The DCDMA includes all metric standards today, but people still refer to DCDMA as the imperial standard. Today, both are included in the ISO system of standards. Other standards have also been created during the years. For example, China is using its own standard called the GB standard. The standardization refers to the dimensions and threads of the drill bits, reaming shells, outer and inner tubes and drill rods, as well as the core springs and core lifter cases. The standards do not cover the threads of wireline drill rods. The DCDMA system, as well as the CMS system, are based on a series of drill hole dimensions. In DCDMA standards, the size of the hole refers to letters, and in CMS, it refers to numbers. For DCDMA, size A has a 47.7 millimeter hole diameter, and for CMS, size 46 has a 46.5 millimeter hole diameter. The core diameter can vary depending on which type of core drilling system is used. The DCDMA system has a total of 6 different main sizes, each with their own letter. The Cralius metric standard has a number of standard sizes, some of which correspond to the DCDMA system. The abbreviations in the DCDMA system include, first, a letter for the size, N in this case, a letter for the company, and some more letters for the design. Here, EX stands for X-Core. The CMS system also starts with the size, before showing a combination for the design. For example, 76T2, where 76 is the size and T2 the design. For each drill hole dimension, there is a set of drilling tools such as drill bits, reaming shells, core barrels, drill rods, and casing tubes that are fully interchangeable. But remember that the threads of the wireline drill rods are not officially standardized. The purpose of core drilling is to retrieve a high-quality core sample. To understand the core drilling process, we will start with the different components of the equipment. Let's take a look at the drill string. A ring-shaped drill bit is armed with diamonds or tungsten carbide and cuts the core sample out of the rock or soil. The drill bit is mounted on a reaming shell, also armed with diamonds or tungsten carbide, which reams the drill hole to the right diameter and stabilizes the bit. The reaming shell is mounted on a core barrel, whose purpose is to collect the core sample. Inside the core barrel is a non-rotating inner tube, which stores the core sample during drilling. A number of drill rods connect the core barrel with the drill rig. Their main purpose is to transfer torque, rotation speed, feed, and lifting force from the drill rig to the drill bit. When drilling in non-stable formations, casing tubes are needed to prevent the hole from caving in. A flushing system flushes the drilling fluid through the drill string. The core drilling process includes 3 major operations: the actual drilling, the retrieving of the core sample, and resuming of the drilling. Together, this is called a round trip. There are 2 core drilling methods, conventional and wireline. The main difference lies in the method used for bringing up the core samples to the surface once the inner tube is full. In conventional core drilling, the entire drill string has to be pulled out of the drill hole in each round trip. In a 150-meter deep drill hole, this could mean that the drill rod threads need to be broken and joined back again up to 50 times for each core sample. In wireline core drilling, A so-called overshot is sent down to release the inner tube. The overshot and inner tube are then hoisted up to the surface with a wire. A new inner tube is lowered down and locked in place. This method is much more productive, efficient, and safe. During the drilling process, a drilling fluid is flushed down the drill string to cool the drill bit and to transport the cuttings to the surface. When the drill bit is worn out, the whole drill string has to be taken out of the drill hole, regardless of drilling method. Therefore, choosing the right drill bit for the formation is extremely important for high productivity. Between each round trip, the driller stores the core samples in core boxes. The driller logs the time and date of the drilling, as well as depth, core recovery, and possible losses. These high-quality core samples are the final goal of the core drilling process. The wireline core barrel consists of three basic components. The inner tube assembly, which consists of the inner tube and the head assembly, the outer tube assembly, and the overshot. The purpose of the inner tube is to store the core sample during drilling. To prevent rotation of the inner tube, the head assembly is equipped with a set of ball bearings. The drilling fluid is flushed via the locking and adapter coupling through the space between the inner and outer tube, passing through the inner tube gap. The inner tube gap can be adjusted using a threaded spindle and a lock nut in the head assembly. For example, in soft and friable formations, the gap needs to be smaller to prevent the drilling fluid from flushing away the core sample. When the inner tube is full, it pushes against the shutoff valve and stops the flow. This will increase the drilling fluid pressure, and it is a signal to stop drilling and replace the inner tube. The core lifter case and the core spring are used to capture and break the core. In hard competent rock, you need a lifting force of 2 to 3 tons to break a B-size core. Thanks to the compressor spring, the outer tube and the drill string can move upwards until the inner tube rests against the shoulder inside the drill bit. The braking force is then transferred to the drill bit and the outer tube. To retrieve the inner tube assembly, there are two types of overshots: surface and underground. The underground overshot is equipped with a packing and can be pumped into flat or upwards directed drill holes. The surface overshot falls down the hole by gravity and is sent down to release the inner tube. When the overshot assembly has released the latches from the locking coupling, the inner tube assembly can be hoisted to the surface. To release the core sample from the inner tube, the driller sometimes needs to tap on it with a rubber hammer. This can deteriorate a soft core sample. To prevent that, a triple tube core barrel can be used, which means there is an extra inner tube inside the normal inner tube. This can be pumped out and then opened in 2 halves to collect the soft core sample. While emptying the core sample, a second inner tube assembly can be reinstalled. The inner tube assembly is fully installed when the landing shoulder lands on the landing ring inside the outer tube and then latches against the lower end of the locking coupling. Without proper latching, the inner tube is loose and will be pushed up the drill string while drilling. To secure a proper latching, most wireline systems are therefore equipped with a landing indicator. The purpose of the drill rods is to transfer torque, rotation speed, and lifting or feed force down to the drill bit and the core barrel. In wireline drilling, since the inner tube assembly is sent through the drill rods, the inside of these rods must be produced with a high quality. Therefore, each wireline core barrel dimension requires the same drill rod dimension. In deep hole drilling, the weight of the drill string increases the requirements on the drill rig torque and lifting force. To maximize the depth capacity of the core drilling machine, special drill rods are designed with a thinner body to decrease the weight of the drill string. Wireline drill rods are made out of a seamless blank of high-quality steel. Either the blank is heat treated before turning the threads, or the blank is threaded first and then the threads are heat treated. Conventional drill rods are made out of steel or aluminum. The steel drill rods are equipped with steel couplings, which are threaded and heat treated or friction welded to the steel body and then heat treated. Since no inner tube needs to pass through the drill string, one dimension of conventional steel drill rods can be used for 2 or 3 core barrel dimensions. The aluminum drill rods are also equipped with steel couplings, but these are threaded and glued to the aluminum body. With only half the weight, this gives the aluminum drill rod almost the same properties as the steel rods, but with higher wear. The dimension of the aluminum drill rods must be adapted to the dimension of the core barrels. Before reaching the rock mass and extracting a core sample, the driller needs to go through the overburden with a casing shoe that drills the hole and casing tubes that prevent non-consolidated formations from caving in. This phase requires casing shoes with diamonds or tungsten carbide, and in some cases, telescopically adapted casing tubes in order to be able to drill as deep as necessary. The DCDMA standard casing tubes have thicker walls than the CMS standard casing tubes and are therefore more suitable for heavy and demanding casing tube drilling. The water swivel connects the rotating drill string to the water hose from the flush pump. There are 2 types of water swivels. One is used on underground core drilling machines with synchronized make and break systems, and the other is used on surface core drilling machines using main hoist. The reaming shell has 2 functions. It reams the hole to its nominal diameter, preventing a new drill bit from getting stuck in a slightly conical hole. It stabilizes the core barrel and mitigates deviation of the bore hole. The drill bit cuts out the actual core, and there are 3 general types, each corresponding to a certain ground condition. Tungsten carbide bits for geotechnical investigation core drilling in soil and in other soft formations. Tungsten carbide is used in the form of inserts, or chips. PDC, or polycrystalline diamond composite bits for core drilling in soil, soft shale, soft limestone, and other soft sedimentary formations. PDC bits are used in the form of buttons, or surface set. Diamond bits for core drilling in medium to extremely hard rock. Natural diamonds are used in surface set bits. Synthetic diamonds are used in impregnated bits. The diamonds are embedded in a matrix. Since impregnated diamond drill bits are the most common bits in exploration, we will put our focus here. First of all, the diamond bits matrix is classified according to its hardness. The general rule is that a softer matrix is used in a harder rock, and a harder matrix is used in a softer rock. For example, in hard rock, the diamonds last a shorter time. Therefore, the matrix needs to be softer to expose new diamonds more frequently when the old ones are worn out. To maximize the productivity, it is therefore important to match the matrix hardness with the rock hardness. It is also important to choose the right drilling parameters, corresponding to the matrix hardness and the rock hardness. For example, if this H-size bit is used in very hard rock with an RPM between 750 and 950, maximum weight on bit, also called WOB, of 50 kN, and water flow higher than 50 liters per minute, you can expect a penetration rate between 8 to 18 centimeters per minute. Following these parameters will maximize bit life. The optimal state is called free cutting and is the perfect balance between weight on bit, WOB, RPM, and flushing. This will give the optimal rate of penetration, ROP, and maximum bit life. Important, providing that you have chosen the right bit matrix for the right ground condition, of course. To optimize the flushing, The drill bits are manufactured with different profiles and waterways. The most common is the ECF profile, suitable for most rock formations. Another one is face discharge, FD profile, suitable for extremely broken, loose, or soft formations, where there is a danger of washing out the core sample. To further extend the bit life, different impregnated heights are available. A height of 13 millimeters is the most common, but both 10 millimeters and 16 millimeters are available. Examination of a used bit can provide the driller with useful information. If the driller is using incorrect drilling or flushing parameters, this can be seen from specific wear patterns on the bit face. For example, too low RPM may result in a concave bit.